Okay, we're going to start talking about topic 6A. So we're going to finally begin our discussion of equilibrium. We're going to see how it's related to the thermodynamics that we've learned so far. So if we want to understand the equilibrium constant, we want to think about the fact that when you reach equilibrium, the ratio of products over reactants is equal to a constant, and we'll see where that comes from. So we remember that a change in Gibbs free energy, if temperature and pressure are constant, is equal to a negative T times delta S of the universe. So if T's in Kelvin, that's always positive, which means if we're looking for the maximum entropy when a process stops changing, that would mean that we're looking for the minimum Gibbs free energy. So if we look at a graph of Gibbs free energy versus extent of reaction, where we've defined this chi to be the change in moles of A is equal to minus D extent of reaction because moles of A are going down. But as the moles of A go down, the moles of B would go up by the same amount. So every time some A goes away, B is formed. So the extent of reaction, you can graph a single variable versus graphing NA and NB because they're related to each other. So if going forward or backwards is going to decrease Gibbs free energy, then that's going to continue to happen until you reach the point at which it stops changing. And then we know we're at this minimum, which would be the same thing as saying we're at a maximum in the entropy of the universe graph versus the extent of reaction. But if we have constant temperature and pressure, we can use the Gibbs free energy. So technically then a change in Gibbs free energy is really equal to this derivative. It's the point at which you're at the minimum. So that's the point at which the derivative equals 0. So then you would be at equilibrium. So how does Gibbs free energy change, and how do we want to think about why it's changing as a chemical reaction takes place? So here's our whole expression. Gibbs free energy changes we saw as a function of volume, or as a function of pressure and temperature, and the proportionality constants are volume and negative entropy. It also changes if you change the moles of A and you multiply that by the chemical potential, because remember, chemical potential is just molar Gibbs free energy of A. Same thing with the chemical potential of B. So it's also going to change if you change the number of moles of A or number of moles of B. We also saw early on that it would change if you change the chemical potential, and chemical potential is a function of concentration, so that could happen. But we saw with the Gibbs-Duhem equation that the chemical potentials always have to change in such a way that this sum is going to be equal to 0, so that if you add it all up, the chemical potential of A goes up when the chemical potential of B goes down. So then if you also add to that the fact that we're going to talk about constant temperature and pressure, then everything's going to cancel in this definition of a Gibbs free energy change, except how it changes as A and B, the number of moles of A and B change. And so if we want to then go back and think about how the equilibrium constant is understood based on thermodynamics, this is going to be where we start. So a change in Gibbs free energy, then if we replace dNA and dNB with change in extent of reaction, remember dNA is equal to minus a change in extent of reaction, because if we're talking about the forward reaction, it's the number of moles of A is going down. And so then if we just group terms, this tells us that dG equals the difference in the chemical potentials of B and A times the extent of reaction. And so if we just take this over to this side, that tells us that the derivative, how Gibbs free energy changes with extent of reaction, remember we got to this point with a constant temperature and pressure restriction, is really equal to the difference in the chemical potential of B and A. So that's the same as we've been thinking about delta G's all along. So this is the molar Gibbs free energy of B. This is the molar Gibbs free energy of A. So in the process of the reaction taking place, the change in Gibbs free energy for the reaction is the difference between the chemical potential of B and A. And so when we reach equilibrium, then we know that in order to have the delta G equal to 0, that must mean that the chemical potential of A at the equilibrium composition is equal to the chemical potential of B at that same composition. And we've talked about that in relation to phases up to this point, that we always know when, for example, a liquid is in equilibrium with a vapor, that means the chemical potential for those two phases are the same. So now we're just extending that to understand that that's also true for a chemical reaction. If the chemical composition stops changing, that must mean that there's no advantage of moving A to B or B to A. And so those two chemical potentials must be equal to each other. So just a couple of definitions. Exergonic and endergonic reactions. So exergonic reaction is one that you could produce work, so that's the same thing as saying it's spontaneous. Endergonic is one that consumes work, so that's the same thing as saying it's not spontaneous, but you could force it to happen by doing work on the system. Let me just see if that can focus a little better. Okay, so now let's just talk about how we can relate the equilibrium composition back to delta G. So if we start with our definition from here, that delta G equals chemical potential of B minus A, we can write the chemical potential of each as a function of what their chemical potential would be if B was at 1 bar versus what it is in my composition for my reaction. Subtract from that what the chemical potential of A would be if it was at 1 bar, and then how it changes as it moves from 1 bar to whatever partial pressure it has in my gas. So we're talking about equilibrium of perfect gases right now. So that tells us that the delta G is going to be equal to this chemical potential of B in the standard state minus chemical potential of A in the standard state. And that's just difference in the Gibbs free energy of everything being in its standard state. So remember, these are Gibbs free energy molar ones, and so this is a delta G is equal to the difference between the chemical potential of B and A when they're in the standard state. And then if we combine these two terms, if you combine them, you have RT, and then you have ln of PB over standard state, and then you're going to flip this one because it's negative, so you have standard state over PA. And so you end up that the delta G for a reaction is related to what it would be if all the gases were in pressure of 1 bar. And then it's different from that based on what the pressure is in your composition of your reaction mixture. So these will all cancel. Notice if I had a reaction with a different stoichiometry, I'd end up with some standard state pressure still in there. We'd still end up with the ratio of products over reactants, we'll see. But remember, if you're working in your standard state unit, so if you're working in units of bar, you don't really have to worry about how many P standard states you have because it's just going to be 1. But realize here they canceled only because our stoichiometry was 1-to-1. So if you want to get the delta G for the standard state so that you could use that equation, you go to the back of the book and you would take the molar Gibbs free energy for B in its standard state minus A in its standard state. So we would be able to use tables. We'll see we're going to actually use delta G's of formation because we don't have absolute values of chemical potentials, but we know changes in chemical potentials. So we are going to define that PB over PA to be equal to Q, the reaction quotient. So this should all be really looking familiar to you. When we're at equilibrium, we know that delta G for the reaction is 0. So we can set that equal to 0. And then we want to solve for what the composition that remains constant at equilibrium would be. So we'll replace Q with K, because it's the reaction quotient, but it's that specific one where we're at equilibrium. And so you see that what makes a lot of sense based on what we've known so far. We know that delta G tells us if a reaction is spontaneous at equilibrium, so it must somehow be related to the equilibrium constant. But if you just rearrange this, you see the direct relationship. It's a logarithmic relationship. And this also is an equation that I know you have used many times. So let's just look at this figure. So if you're graphing Gibbs free energy versus extent of reaction, it would end up being just a straight line going from the chemical potential of pure A to pure B. But because when we mix, remember when we mix two perfect gases, the chemical potential always is lower for the mixture because each of these is each of these is negative because mole fraction is less than 1. So we have the mixing depends on the composition. And when you add that into the picture, you do get a graph where Gibbs free energy with extent of reaction has a minimum in it. And so you could figure out where the minimum is and therefore where equilibrium is. So for any general reaction, you can go through that same process and you're going to end up with a reaction that, or an equation that looks very similar. You're going to have the difference in Gibbs free energy for everything in their standard states. But if we have A's and B's going to C's and D's, remember each of these would be, I should write that out. So each of these guys they're perfect gases. Yeah, the activity for a perfect gas. So with activities, you don't have to worry about this because the activity of a perfect gas is equal to the partial pressure of C over the standard state pressure. So as long as we're working in activity and not concentration, this really I don't need to talk about right now. Sorry. So you guys should stop and do self-test 6A.1. And you're going to start by calculating the delta G standard state for the reaction by doing delta G's of formation of products minus reactants out of the table. And then you're going to put it into this equation to get the equilibrium constant. So just take a little while to do that to refresh your memory on how you calculate thermodynamic properties from thermodynamic properties for formation. Okay, so the equilibrium constant written in activities, which would mean you're assuming that you might not have ideal behavior. So you could write the activity as the activity coefficient times if you're working in units of molality times molality. So we're just pulling them apart. So you'd have all the activity coefficients and all the concentrations you put in. So you could think about writing an equilibrium constant in terms of the activity coefficients times what you have. And if you think about splitting it this way, it helps you use experiment to try to figure out what the activity coefficients are actually. So the other relationship between equilibrium constants that is important is if we're talking about gases, oftentimes we want to report the equilibrium constant in terms of concentrations. And with gases converting from pressure to concentration, it makes most sense to go to molarity instead of molality. And you'll see when we look at the ideal gas law here. So if we look at a K, so a K is always going to be in units of bar if you get it from a delta G out of our tables, because our table, the standard state is 1 bar. So if you want to convert all the pressures into molarity, just rearrange this, and the number of moles over the volume, if you're working in the right units, will be molarity. So if we look at a K that's for this reaction, it would be PB raised to the little b over PA raised to the little a. So if you wanted to convert that into a KC, you only can do it if it's gases, of course, because this only applies to gases. So only for gases. Then we're going to convert each of the pressures into molarity. So we're going to do that by dividing them by RT. So it's going to be the equilibrium constant in pressure units, and then you have to multiply each pressure by 1 over RT. So you'll have B of those in the numerator and A of those in the denominator. So if you group them together, it will be the equilibrium constant in terms of pressure times 1 over RT raised to the B minus A, where B minus A really is just the change in number of moles of gas for the reaction. So this first topic stops here with just a little discussion about the molecular interpretation of the equilibrium constant. And so let's first look at this. So if delta G is related to K, you can rearrange this and solve for K after you take each side and raise E to it. And then if we remember that delta G is related to delta H and T minus S, then we can replace delta G with delta H minus T minus T delta S. So with the negative out front, you get negative delta H plus T delta S. And if they're both divided by RT, you see that the equilibrium constant is both a function of the delta H of the reaction and the delta S of the reaction. So when we look at this graph, it shows us, it's a little bit complicated, but it shows us that if you have two reactions that are endothermic, okay, they're both endothermic, but on this side, it turns out that at equilibrium, you have about equal populations of A and B. Ooh, and that's because this is A on this side and B on this side, the population of states. So the green represents B and the pink represents A. So it represents, when you look at this in the middle, how many states are populated. So what this shows you is the states for B or A are about equally spaced, and the states for B are also about equally spaced. So when you look at the population of states, they're going to be, yeah, so in the end, it turns out because it's endothermic, you have all of these population of states at lower energy for A, and then you continue up, and B's states are as populated, but you don't have as many because you had to put energy in to get up to this point. So you're going to have equilibrium that's dominantly A, whereas over here, it's different in that A states are fairly far apart. B states are really close together. And even though B's energy is much higher, where you'd start to populate the energies of B, when you look at it, because these states are so close together, you get more population of states for B. And population of states is really a measure of entropy. So that's really saying that entropy is driving this equilibrium to be closer to B than to A. Whereas over here, you would say delta H is really driving equilibrium to lie closer to A, because the population of states is about the same, but so many more states in A are populated because it's at a lower energy than B. So if that has any confusing parts to it, we can talk more about it in class. Okay, so that's it for A.